Hi guys, my name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us to my discussion for today and kindly request our members to subscribe, engage us in the comment section and also ring that notification bell to be getting updates on our various discussion under the broader concept of mechanics. Now in this case, I'm going to look at the second part of the concept of rigid bodies, and this is going to be complementing on our previous discussion whereby we looked at the concept of dynamics of rigid bodies in details. Now, in this particular case, we shall have a small recap, which is going to assist us define this concept of linear momentum. And of course, it's going to be giving us a way of trying to do other subsequent discussions on, of course, trying to pick up on some of the basic concepts which we need. Now, in this case, we had defined basically a rigid body as a collection of particles, which of course is going to be having a property in a way that the distance between the particles are going to be remaining unchanged. And that's going to be described in the course of motion of these specific rigid bodies. And therefore, we said that if we are going to look at the concept of rigid body dynamics, and therefore this is going to be discussing on the concept of motion of this specific type of bodies. And we have described various range of motions which we basically gave in terms of the degrees of freedom. And we said that just different from particles which are going to exhibit 3 degrees of freedom, the rigid bodies are going to have 6 degrees of freedom. And in this case, given an illustration of the Cartesian coordinate system, which is going to be giving us a translation in the x, y, and z, of course, which are going to constitute 3 degrees of freedom. And apart from that, for rigid bodies, we said about other additional concepts which included the concept of rolling, which we gave as a roll axis, the concept of a yaw, a motion, and then we had talked about the concept of a pitch. And this case, I had given an example of an aeroplane, which is going to be at a stationary position, which is going to exhibit the concept of either rolling, yawing, or pitching in that specific case. And apart from the 3 which we had considered for the Cartesian coordinate system, of course, this is going to be giving us 3 additional degrees of freedom, which is going to compound together form the degrees of motion of a rigid body. Now, in this case, I consider this specific aspect of a plane to be an example of a rigid body, and that therefore gives us a set of independent displacements or rotations which we have seen, which specified the displacement or the, of course, the formation or of position of that specific aeroplane, which we considered in terms of the degrees of freedom. Now, basically, then therefore said that we're going to consider this one by having various types of motion which are going to be exhibited by these rigid bodies. And in this case, I specifically talked about 2 types of motion which we can give in this specific example. And this is going to be constituting a translational motion, which I've given in terms of an example for a Cartesian coordinate system. And then we're going to look at a second part, which we had, of course, said in terms of the rotational motion, which I've given using these 3 independent sets of displacements given as such. So in this case, we are going to have this one as a rotational motion. And therefore, we said that this particular rigid body is going to exhibit these 2 types of motion. And I'm going to have an additional information of especially this specific concept of motion, which we had basically mentioned in summary form in our previous discussions. Now, for translation, we're going to see that these are particularly going to be movements that are going to change the position of this specific rigid body. And of course, we're going to see that in trying to consider the concept of translation, we're going to see that the position of course, a particle in this specific object is going to be remaining the same, whereby we're going to see that basically the lines which are going to join these specific particles are going to be described as either, of course, rectilinear or curvilinear, given in this particular case. So I'm going to use this specific demonstration. So in this translation type of motion, we can have this specific particular orientation of the particles going to remain the same. But in the course of motion, we're going to see that we can describe the path taken by this particular object using this curvature. And therefore, this kind of motion is going to be referred to as curvilinear. My spellings are correct in this case. So this is going to be referred to as a curvilinear type of translation motion. But if we are going to have this specific a point of connection between the dots being given by parallel lines which are going to be given as such, of course we are going to describe this one as a rectilinear kind of a translation for the translation kind of a motion given as such. So this are going to be forming a section, particularly a division of this specific translation form of a motion. And of course, for rotational motion, this is going to be a unique one whereby we're going to see that for a rigid body that's undergoing a rotational motion, this is going to be moving in a circular path about an axis. And of course, as we had described this one, this is going to be a motion from a single point. So therefore, we're going to have this one as a point of motion. If we consider this specific illustration to be the case, then therefore we're going to have this one exhibiting what we refer to as a rotational motion about an axis given as such. So these are the types of motion which we have, of course, mentioned, which we're going to take into consideration. And therefore, that's going to be assisting us in trying to describe the various aspects, like the, of course, linear momentum of these particular rigid bodies. Now, in this case, we're going to look at this specific aspect of the linear momentum. And in our previous discussion, I've stated that for us to describe the concept of dynamics of rigid bodies, we're going to rely on a number of theorems. The first one, which was the principle of course, angular momentum, and then the second one was the principle of linear momentum, and of course, the last one was the principle of conservation of course, energy, which listed in my previous video. Now, in this case, for the linear momentum, I mentioned that we are going to describe this specific concept of linear momentum given as the first derivative of the product of a mass and of course, the product of mass and this position vector we are going to give in terms of r, and therefore this is going to give us an implication of the product of mass and of course r given in terms of that second derivative. And of course, this is going to be giving us the concept of a force. Now, in this case, I mentioned that basically we're going to have this one as the total mass of that rigid body, and F is going to be the external forces which are going to be involved in this specific aspect of motion of this rigid body. And of course, we're going to have r as a position vector given in terms of so this is going to be a position vector given in terms of that particular representation of r, which is basically a position vector of the center of mass of this rigid body with respect to the origin. And I said that we're going to consider this specific description of the motion of a rigid body using the Cartesian coordinate system, whereby in my wording of the term origin, of course, is going to be concerning this particular center of reference we are going to use, of course, using that Cartesian coordinate system. And in this case, then, therefore, we can look at other ways in which we are going to describe this specific aspect of linear momentum by trying to consider, of course, the properties of linear momentum, which is going to be the same as those of angular momentum. And in this case, we're going to use Newton's second law of motion and third law, of course, which are going to assist us in finding a derivation for this specific formula which I've given on the board. And in this case, we're going to consider Newton's second law of motion. And from that specific motion, we're going to see that this motion basically deals with the rate of change of momentum, or what we refer to as linear momentum. And this is going to be the rate of change of linear momentum of this particular particle is going to be, of course, given as this specific derivative. And of course, we're going to see that this is going to be constant, having this specific aspect of a constant. Now, we have described the concept of momentum from our previous discussion as the product of mass and velocity given as that one. And of course, we're going to consider this aspect with the sum of all the forces which are going to act in this specific particle of a mass given as m. So we're going to consider this specific particle of a rigid body having a constant mass given in terms of m. And therefore, from Newton's second law of motion, the rate of change of linear momentum of this particle with constant mass m is equal to the summation of all the external forces acting in this specific object. And therefore, from this one, of course, we can have this particular derivation given in terms of the rate of change of momentum of a particle of a constant mass is given as the summation of all the of external forces which are going to be given in terms. So we're going to give this one in terms of N, whereby we're going to have a sum of these specific forces given as Fi given as such. So this is going to give us some implication of Newton's second law of motion. And of course, we're going to have this one as well given in terms of this specific aspect of a force or momentum, which I've given in terms of the product of course, M and V. Therefore, implying that this specific rate of change, which is equivalent to the summation of the forces which have given all the external forces which have given, of course, we can give this one in terms of this particular representation of the first derivative with respect to time of this product of mv, whereby aside this, I said, of course, this is going to depict the concept of a momentum given as such. So in this case, therefore, this is going to give us a direct relationship between this one and, of course, these forces which have given. And generally, we're going to see that this specific body is going to be a finite mass that is composed of a number of particles which we can give in terms of n. And therefore, in order for us to evaluate the type of forces, both either external or internal, being involved in this kind of motion, we're going to consider an infinitesimal mass of this particular, of course, object given in terms of, so this is going to be an infinitesimal mass of this particular object, which is going to consist of the constant mass over m. So this can be given in terms of a sigma m given as that one. So for us to find the representation of this specific aspect of the forces involved, we're going to have this sigma m with the second derivative of the position vector given as that one, all over, of course, we're going to have this one given as that one. And of course, from the previous formula which I had given for linear momentum, which we had stated, of course, we're going to derive meaning from this specific representation. And therefore, this is going to constitute all the internal and external forces given in terms of the summation from the first one to n given as such of the forces is equivalent to. So the first term of this specific section of the equation on my right is going to be considered basically different from this one, and I'm going to elaborate on this one. So this is going to be the external forces which are going to be involved in this case, and of course we're going to have this one as the internal forces which are going to be acting on this specific object. So in this case, we are going to consider, if this is the case, then therefore we're going to consider Newton's third law, which is going to be explaining on the concept of internal forces of an object such as this object under consideration. And of course, these internal forces are going to sum to zero. And this case, therefore, we're going to consider this specific aspect, whereby this is going to be affected by Newton's third law of motion. And of course, we're going to see that we can have this specific version of the equation given in terms of the second derivative with respect to time of this specific summation which we had done. So we can give this one in terms of an integral over rdm is equivalent to this external forces which I've given in this particular case. Now, in this one, I've said that in consideration of Newton's third law of motion, this is going to be equivalent to zero. So therefore, this specific, of course, summation is going to refer, or this specific product of the infinitesimal mass and the second derivative with respect to the position vector is going to give us the external forces, which are going to be given in terms of the summation of forces from the first to n of the external forces which are given in this particular case as this particular representation. Now we can do, of course, what we call, of course, a manipulation of the first section of this particular equation. And we're going to have, if we consider the total mass given in terms of m, we can introduce m in this particular case and have this manipulation of this equation by introduction of m. And of course, this is going to be given in terms of that one. So if we introduce m as of course, a numerator and a denominator at the same time, this is going to be just imply that we're going to maintain our equation given as such one, and therefore this is going to be just the same. Now the second part of the equation which I've given in this particular case is going to be representing the integral over rdm, small m over, of course, total mass given as that one. And this is going to refer to what we call, of course, the center of mass of this specific, of course, object. And this is going to be denoted using RCM given as that one. So in case we come across this particular notation in our subsequent discussion, and therefore that's going to be assisting us in trying to define the concept of the center of mass. Now, in other versions, we're going to come across this aspect of the center of mass given in terms of this specific representation, which is going to be given in terms of x bar is equivalent to the summation of these specific elements of mass, which is going to be mi, and then this is going to be with the product of this, of course, position vector given as xi all over m. And this is going to be giving us what we refer to as the position, of course, the center of mass given as this one. So in this case, in case we come across this specific representation, then therefore it's going to be okay for us in trying to represent it as such. Now, I hope that in case we come across this specific, of course, aspect, we're going to represent the concept of linear momentum as I've just described on the board, and it's going to giving us a theorem in a sense which we are going to rely on in trying to evaluate the concept of linear momentum of rigid bodies, and thereby describing the concept of their specific motion. Now, in this case, I'm just going to be creating an emphasis on this specific first description. So it's going to create for us a summary. This is just an elaboration part which I've just been doing on the board. So we're going to have this one as a representation of a linear momentum, which is going to be equivalent to the forces which I've just mentioned. So in this case, in case we come across this one, then therefore it's going to be giving us, in an essence, the concept of a linear momentum, whereby this is going to be forming the total mass. This is going to be the position vector of the center of mass of this rigid body relative to the origin. And in this case, I'm going to represent this one in terms of perhaps the two Cartesian coordinate system given as such. So I'm going to have this specific xy Cartesian coordinate system, and in case we have a point P with reference to this specific object, then I'm going to have this another Cartesian coordinate system. So this point is going to be relative to the position of this specific system, bearing in mind that this 0 is going to be the origin with respect to that. So we're going to consider n2 points, perhaps P and X, with respect to this specific point which we refer to as an origin. And therefore, that's why I'm regarding this specific position vector as a position vector, which is a position of the center of mass of this particular body relative to the origin. Now, I hope that is understood. Kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell to be getting updates on various discussion we do in maths and sciences. So that is it for now, guys. By God bless. We'll catch us in our next video.